Insertion sort is a simple sorting algorithm that works by building up a sorted array one item at a time. It is efficient for small arrays and arrays with partially sorted elements. The algorithm works by iterating over the array and comparing each element to the elements that come before it. If the current element is smaller than the element that comes before it, the algorithm swaps the current element with the element that is left of it in the array. The process is repeated until the current element is in the correct position. The general concept of how the algorithm works is as follows. Start by assuming that the first element of the array is sorted. For each subsequent element in the array, compare it to the elements that come before it. If the current element is smaller than the elements that come before it, swap it with the first element that is larger than it. Repeat the process until the current element is in the correct position. Move on to the next unsorted element, and repeat the process. We will take a look at an example using selection sort, and then talk about the complexity of this algorithm. Example 1. We will use the array consisting of 4, 2, 3, 6, 2 in this example. We first assume that the first element in the array is sorted. This is represented by the green outline. We then check if the second element in the array is smaller than the first element in the array. We swap them if this is true. 2 is smaller than 4, so we swap them. We can extend the green outline since, for as far as we know, we have sorted the first two elements. We now take a look at 3 and 4. We swap them since 3 is smaller than 4. We then have to check if everything within the green line is still sorted. We do this by checking if 3 is smaller than 2. Since it's not, we don't swap and extend the green outline. Next on our list is comparing 6 and 4. We don't swap these elements since 6 is larger than 4. We again extend our green outline. We now have to compare 2 and 6. Since 2 is smaller than 6, we swap them. We have to check if everything inside our green outline is still sorted since we just swapped 2 and 6. We do this by comparing 2 and 4. 2 is smaller than 4 and therefore we swap them. Since we just made another swap, we have to again check if everything in the green outline is still sorted. Therefore we compare 2 and 3 and swap them since 2 is smaller than 3. Next up is the check if everything is still sorted within the green outline. This is done by comparing 2 with 2. We don't swap these elements because 2 is not smaller than 2. We can now extend our green line since we know that everything has been sorted. Time complexity. The time complexity of insertion sort is n squared, where n is the number of elements in the list. This makes it inefficient for large lists, but it is still a useful algorithm in certain situations, such as when the list is already partially sorted or when the list is small. In the best case scenario, the input is already sorted and the algorithm only requires n1 comparisons, making it an O(n) algorithm. However, in the worst case scenario, the input is sorted in reverse order and every item must be shifted over to make room for the new item, leading to a total of n times n-1 divided by 2 comparisons, making the algorithm O(n squared). We will take a look at an example with this pseudocode of insertion sort to get an idea of why this algorithm has a complexity of n squared. Example 2.